We would like to introduce our MLCC type all-solid-state lithium-ion secondary batteries. Lithium-ion batteries are widely used because of their large storage capacity, which enables portability of many electronic devices. However, they do have technical issues that include safety and electrical. Regarding safety, there is the risk of explosion and ignition that could endanger human lives. This issue is due to electrolyte, a flammable liquid that battery cells contain. One solution to solve this issue is by replacing the liquid electrolyte with a solid one, creating an all-solid battery. The diagrams here illustrate the internal structures of both batteries. You can see the previous structure of the lithium-ion battery with a liquid electrolyte, and the new structure of the all-solid battery with completely solid electrolytes. Previously, with lithium-ion batteries, charging the electricity supplied from an external power source caused lithium ions in the positive electrode, called an active material, to move to the negative electrode, where they are received by the active material of the negative electrode, thus charging the battery with electric power. When discharging, the lithium ion returns, thus generating electric power from the external source. There is a separator in the electrolyte, which prevents a short circuit between the positive and negative electrodes by allowing only lithium ions to move between the electrodes. In comparison, in an all-solid battery, a solid called a solid electrolyte serves as both an electrolyte and separator. These properties are realized by positioning the solid electrolyte so that it physically separates the positive and negative electrodes, forming a solid electrolyte of materials that allow only lithium ions to pass. By removing the flammable liquid, it is possible to build a safe battery that removes the risk of explosion and ignition. As previously mentioned, the key advantage of a solid electrolyte is safety, without the risk of explosion or ignition. However, another advantage is stability. An all-solid battery, which is made of chemically stable inorganic ceramic, maintains its initial performance for a long time after repeated cycles of charging and recharging. In addition, a battery with a liquid electrolyte constantly has the risk of leakage, especially after a long period of use. On the other hand, an all-solid battery has no such risk and can be used for a long period of time. In principle, using the same method of producing multi-layer ceramic capacitors, chip batteries of any size can be manufactured. These photos show the samples of the multi-layer all-solid chip batteries that were exhibited at CTEC in the past. As you can see, batteries ranging from relatively large size down to 1 millimeter or smaller can be created. We are currently developing two types of all-solid batteries. The left side of the slide shows the polarized type, operating at 3.2 voltage, and on the right is the non-polarized type, operating at 2.4 voltage. Both of the charts show the typical characteristics of each type. Showing the voltage curves while charging and discharging for 5 hours each at room temperature reveals that the average operating voltages are 3.2 voltage and 2.4 voltage. The batteries were found to have no additional side reaction and could maintain a high voltage until the capacity is used up. In the future, we will continue our commitment to develop batteries with greater capacities. Here is the result of the pulse discharge test, which evaluated the response from the 2.4 voltage battery types. The test compares the characteristics of our all-solid batteries to that of liquid button batteries in severe environments at low to high temperatures and under pulse discharging. In both cases, when instantaneously discharging a large current, a voltage drop occurs. However, the all-solid battery has a smaller voltage drop than that of the liquid button battery. As shown, liquid batteries indicated large voltage drops at low temperatures, but all-solid batteries experience only small voltage drop at temperatures as low as -20 degrees Celsius. For high temperatures, liquid batteries are not guaranteed to operate at above 60 degrees Celsius, but all solid batteries can operate at 100 degrees Celsius without any problems. As shown, the test demonstrated that all solid batteries could operate normally under relatively severe conditions such as low, high temperatures or pulse discharging. Our all-solid-state batteries under development can be used for various purposes, with features including excellent safety, stable operation under different conditions, and ultra-small footprint. These batteries are ideal for wearable devices, devices used in severe environments, and IoT devices. This photo demonstrates how all solid-state batteries can be applied on an energy harvesting device. Our dye-sensitized solar cells will generate power to charge our all solid-state batteries. Thus, when power is not generated, the charged power will be used to wirelessly send data gathered by a sensing device through a BLE module. Our all solid-state batteries is suggested for this type of standalone device. For other uses, we would like our customers to consult with us and develop products that fit their needs. Here are the specifications of the initial mass production lineup, which are currently under development. The case size for the products will be 4532. There will be two types of driving voltage, 3.2 voltage and 2.4 voltage. The 3.2 voltage product is polarized with a current capacity of 1 ampere hour. The 2.4 voltage product has lower voltage and capacity than the 3.2 voltage product, is non-polarized, and can be mounted in either direction. Both of the two types have operational temperature range from -20 degrees Celsius to 100 degrees Celsius and above. Customers may choose either type depending on their operating environment. That is the end of the presentation. Thank you for listening.